Okay, this hopefully is working. Hopefully I don't have to redo this again. This is my review extra credit video. I was assigned lecture 32, which is the first lecture on enthalpy and Hess's law. So I'm going to try and share my screen here. Love. I'm pretty sure that worked. Okay, should I make it? We'll try. We'll try to make it full screen. Oh yeah, let's go. Okay, so here we go. Hopefully this is helpful. I'm by no means an expert, but I tried my best to learn it and be able to teach it. So what is enthalpy? We have this H equals internal energy plus pressure times volume. This pressure volume it's a constant pressure. So keep that in mind. But what's tricky about enthalpy is that it's not like a real number. It's more of like an intermediate number we use to calculate other things. So that can get confusing. But the way he broke it down in lecture was that we have this equation, delta H, and we know that, well, the change in delta H is equal to the change in internal energy plus the change in PV. And since we know from past lectures that the change in energy is equal to heat plus work, and we know that work is equal to negative P delta V, we can substitute that negative P delta V for W, and we end up with this delta H equals QP. So let me say that again. The substitutions are going to be for delta E. So that first substitution is going to be this, is going to go in right in here. And then we're going to further substitute within this with this negative P delta V. And this P delta V and this positive delta PV are going to cancel out. And so we're just left with this delta H equals heat. That makes sense. So there are a couple different uses or subscripts for this enthalpy. We have the enthalpy of vaporization, enthalpy of fusion, enthalpy of formation, enthalpy of reaction, and bond enthalpy. And the two we focus on in this review is going to be the enthalpy of formation and reaction. Now this subscript kind of looks like a degree sign. It stands for standard conditions. Now this is very confusing at first, but just put it in your mind that standard temperature and pressure, which we talk about a lot, is not the same thing as standard conditions. Standard conditions is when pressure is at 1 atm and temperature is at 298.15. At standard temperature and pressure, the pressure is actually the same at 1 atm, but temperature is at 0 degrees Celsius, not 25 degrees Celsius. So that can get kind of tricky, but it's really important to not confuse those. So standard conditions is what we use for enthalpy of formation. Another note here is we also use standard state. So we're going to be using the most physical or the most stable physical state under standard conditions. So that would be like for carbon, it's going to be its solid form of graphite. And then also another note is that when we're dealing with solute concentrations, it's always going to be 1 molarity for solutions. Okay, so enthalpy of formation, which is this right here, delta H sub F, this little subscript. So there's very strict rules for this enthalpy. You have to follow all of them, and if you don't, it's not enthalpy of formation. So the first one is you have to have 1 mole of your product. If this over here was 2 NO2 or 3 NO2 or 3 CaO, it would not work. It would not count as enthalpy of formation. It also has to be in standard state. So in the question, it would say like under standard conditions or standard states. Standard states meaning the form, the physical state that it's in. And also lastly, your reactants need to be formed of pure elemental species. So as we can see here, this is nitrogen gas, oxygen gas, and those are both pure elemental species. Same with this one here and here. If we had any compounds as reactants, then it could not count as enthalpy of formation. But we can have compounds on the product side. That's fine. We just can't have compounds on the reactant side. Now, also, I want to point out that there are fractions, which is normally a big no-no in writing chemical equations. Hold on 1 second. Okay. So the reason we can use fractions is because we can only have 1 mole of product. And so if we have more than 1 mole of product on this side, we're going to have more, if we have more than 1 mole of reactants on one side, we're going to have more than 1 mole of products on the other. So that's why we have fractions, because it's less than 1. So just remember, I don't know if I explained that well, but in enthalpy, you can have fractions as coefficients in equations. Moving on to enthalpy of reaction. Enthalpy of reaction is energy released from a reaction as it's written. And this heat released is proportional to the amount of reactants. So what that means is if you double the reactants, you double the amount of heat released. So in this example here, we've got this chemical equation. And we have our amount of heat released is negative 2,877 kilojoules. Then when we double all of the reactants and products here, we also need to double the heat of the reactant. So we double this and notice that it stays negative, but you just multiply that by 2, and this is exactly double of what it was in the first. So just remember, in heat of reaction enthalpy, you have to, if you're going to double the amount of reactants, you need to double the amount of energy released. They're just proportional. So some delta H rules I want to point out that are very important. They come in handy a lot. Your sign changes if you reverse your chemical equation. So let's say you're trying to come up with a product of O2, and this is the chemical equation you're given. Well, obviously the O2 is a reactant on this side right now, not a product. So we could flip the equation to where O2 is on this product side. And in doing so, we just need to remember to switch the amount of, or we just need to switch the sign on this delta H over here. And it doesn't matter like what you're focusing on switching. If you switch the reactants and products either way, it needs to be switched. The sign needs to be switched. And I think the reason for that is because you're changing whether the reaction is endothermic or exothermic. So here, this reaction is endothermic. And because you're flipping the order of what's happening, it's like you're breaking something down, then it becomes exothermic. So when you change the order of the process, whether it's endothermic or exothermic also changes. That doesn't say the same. And it's always opposite. That's why we always flip the sign. If coefficients of reaction are multiplied, the second rule, this is the second rule. If coefficients of reaction are multiplied, delta H is multiplied by the same amount. So basically it's just this idea that if we have this equation NO equals N2 plus O2, and we multiply the whole thing, we multiply this above equation by 3, we also need to multiply this delta H by 3, and that's just because they're proportional. So not too complicated, pretty straightforward. All right, moving into Hess's law. So for an enthalpy reaction, um, we cannot isolate the reaction when it is an incomplete combustion. So in an incomplete combustion, we get this product of carbon monoxide, which makes the amount of CO2 immeasurable. So the way we get around this is because enthalpy is a state function, meaning it doesn't matter what way you get to the product, as long as it's the same product. So you could use 3 different reactions to get this product of 2H2O, or you could use this one reaction to get the same product of H2O or 2H2O. It doesn't matter how you get there as long as it's the same net result. And that's why we can get around this incomplete combustion reactions. So in this example here, as I was saying, the product is the same for both reactions. It can kind of be misleading at first. You have to get used to understanding that these reactions like cause one another. So this one happens first, and then the product becomes the reactant and makes this. So it's 2 reactions to get the same product, but it's the same product in both instances. Thus, if we knew the delta H's of these 2 reactions, we could add them together and we could find the delta H of this reaction. Okay, so kind of what I was just saying, using enthalpy of formation to find enthalpy of reaction. I kind of put it into words because sometimes this equation can be confusing. But so in order to go from an enthalpy of formation, which is kind of like a given, you'd find it on like a formula sheet. It's not something you calculate. To find the enthalpy of a reaction, you take the sum of enthalpies of formation, which you'd find on a sheet in the back of your chemistry book, of the products, specifically the products, and you multiply that by the number of moles of the products. Then you do that, and you sum those all up. Then you subtract that from the sum of the formation enthalpies of the reactants times the number of moles of the reactants. And you can find these delta H values, as I was saying, in the book appendix, and they should be provided for you. Another note I want to say is that if you're trying to calculate the delta H of formation of an elemental species, it's always going to be 0. So it's not going to be listed in the textbook. You just need to know that when it's an elemental species, it is going to be 0. And I wrote that again here. I love this slide. I'm obsessed with how cute it is. But elemental species have delta of formation of 0, and they can be found in the appendix, specifically on pages 18 through 24. If you want to reference that, it's quite a long list. Okay, so I'm going to go through some practice problems. These are actually from the smart work for this lecture. I didn't want to use the same practice problems from lecture, and it was hard to find ones that were applicable to what we were talking about online, so I figured I'd use the SmartWorks. And I'm pretty sure that for some of these, the numbers are different, so hopefully you'll get your own, or you've already done them by the time this comes out. So for the given information below, write an equation for the enthalpy change in reaction 3. So we've got reaction 1, reaction 2, and we're looking how reaction 1 and 2 can get us reaction 3. So we're looking for the delta H of 3. So we know from Hess's law that when we add 2 equations, we can get a third. We talked about that before. So we need to add equations 1 and 2 to get 3. But we run into a problem here because in this reaction of f of s and f of g, g is a product and s is a reactant. And so we need to rewrite the second reaction to flip it, to make f of s a product and f of g a reactant. And we can do this because equations are reversible. But when we do so, we have to remember that we need to make the sign of the enthalpy negative, the heat of the reaction negative. So now this is going to be negative. So going back to reaction 1, it also needs to be reversed because we're trying to end up with f of s. And so when we did that, we switched this, so now it's f of g is equal to f of s. I wish I could write on this. Can I write on this? Oh, I think I can. Yes. That would be so advanced of me. Wow. Okay. So now this is, I don't have a mouse, so this is not going to be my best writing. But now it's it's f of oh cute, f of g is equal to f of s, which is good because in this reaction that we're trying to get, the product is f of s. So we know we're on the right track. And I kind of went backwards. Typically, you'd probably want to start with reaction 1. Sorry, you can just speed this up when you're watching it. But so now we have this reactant of f of g, but in this equation, f of g is also a reactant. And kind of think of it as like a chain of events. So we also need to flip, and this d of s and e of g is on their product side, when in our final it's on the reactants, and it's on the reactant side. So we're going to flip these. I'm not going to write it, but flip these. So then it's kind of more of a chain of events. So it's going to be going d of s plus e of g is equal to f of g. And then we take that product and turn it into reactant, and we go from f of g equals to f of s. And that is the same net result as reaction 3. So we know we're on the right track. So because we have to flip both of these equations, they both become negative. And so it is going to be right here, delta H3 is equal to negative delta H1 plus negative delta H2. I hope that made sense. Okay, practice problem number 2. Chlorine oxide plus O3 equals chlorine plus 2O2. And then we have 2O3 equals 3O2. Then we have their heat reactants here. Determine the value of heat reactant for the following. So it's important to look at what we're trying to find. And we're trying to find the heat of the reaction where the products are ClO and O2. Those are the products we're looking for. And in these equations, ClO is on the reactant side, but O2 is on the product side. So this equation is already set because O2 is on the product side. That's what we want. And so we don't need to flip the sign on this formation reaction. On the one above, however, it's on the reactant side. So we need to flip the equation. And in doing so, we need to flip the sign over here. So this becomes positive. That's a plus sign. Then we're going to add these two together, and we're going to get our answer. So it's pretty simple. All right. Moving on to practice problem number 3. This one is a little more tricky. Use the following information to calculate the amount of heat involved in the complete reaction of 5.3 grams of carbon to form PbCO3 in this reaction for. Be sure to get proper sign with your answer. Okay, so we are looking to find the same product as reaction 4. So we're looking to end with PbCO3. So let's go through the chain of events. We've got Pb plus O2 equals PbO. Okay, let's see what we've got in this next one. Then we take carbon plus oxygen, and that gives us CO2. Okay. Now we have PbCO3 is reacts to form PbO plus CO2. But we have this product that we're looking for. We need reaction 3 to end in a product of this. So what we need to do is flip reaction 3 to get PbCO3 on the product side. And in doing so, we always need to flip the sign. So 86 becomes negative 86. So let's go through our chain of events again. So in reaction 1, we form this PBO. In reaction 2, we form this CO2. And in reaction 3, we use what we formed in the first 2 reactions, PBO and CO2, to form PbCO3. And that checks out because it gives us the same net result as reaction 4. So then, now that we have all of our correct signs over here, all we need to do is add these up, and we're going to get the change in heat of reaction 4. So yeah, that's that problem. Oh, no, not done. That's not what the question's asking for. Now that we have the heat of the reactants, it's asking for the amount of heat to get 5.3 grams of carbon. I did this the first time. Forgot to do this the first time I did this problem as well. So we need to remember that heat of reaction is always measured in kilojoules per mole. I am not good at writing this out. Okay. I don't know why I did that. Okay, so it's always measured in kilojoules per mole. So we need to take the sum of these numbers and convert it to moles. First what we could do, yeah, this makes more sense. You would convert the grams of carbon into moles, and then that number of moles into kilojoules per moles. I think it's on the next slide. It'll make more sense that way. Yeah. So we convert 5.3 grams of carbon is equal to 0.441 moles of carbon, which is just molar mass. Wish I had a mouse. Oh my gosh, it's hard to do. So we got 5.3 grams. I'm going to write this very shorthanded. It's just molar mass, but in case, anyway, we got 12 grams of, and this is carbon. That's the molar mass, and that's 1 mole. Okay, and that equals 0.441. I'm not going to write it. But then we take that 0.441 moles, and this was the sum of our change in heat reactions. We multiply those together, and we get the amount, not just the amount of heat from the reaction, but specifically for the amount that was needed for 5.3 grams of carbon. All right, so that's basically the end of what I have. Some things to remember, that equations are reversible, and that when you do reverse one, you have to flip the sign of delta H. That's very important. It's easy to get confused, but it could help you if you're kind of thinking about if a process is endothermic or exothermic, and you can kind of go from there. You can multiply equations to get mole ratios, but you also have to multiply the delta H. It's basically if you're doubling the mole ratios of an equation, double delta H. Remember HESS'S law, that formula we talked about earlier, and then practice makes perfect. Going through different questions, thinking them through, talking about them out loud, all can help you. Again, I'm no expert. I hope this helped in some way, at least to just kind of refresh topics for you. So yeah, I think that is the end of my review. You can let me know if you have questions, and I'll try to help you out the best I can. Thanks.